Welcome. My name is Thomas Stolbeck. I am a former PhD student at MIT in the Laboratory for Information and Decision Systems. Today I will be presenting some of my thesis research that I conducted with my advisors, Dr. Brooke Schrader and Professor Eitan Modiano. The topic of this talk is learning algorithms for scheduling in wireless networks with unknown channel statistics. So to dive directly into it, in stochastic network control, we must schedule simultaneous transmissions to do basically two things. One, support stochastic network traffic throughout the network, and two, to avoid collisions between interfering links. In order to do this, we must take into account the channel's time-varying capacities. So from the seminal work of Tassio Lewis and Ephremides in 1992 and 93, we know that the max weight scheduling algorithm is throughput optimal. What this method basically does is it schedules transmissions to maximize the product of the channel capacity and backlog. Now, in the case where we don't know the instantaneous channel states, this translates to basically scheduling transmissions to maximize the product of the mean channel capacity over time, multiplied with the instantaneous queue backlogs instead. But what if we don't know the channel state or statistics? In this work, we examine learning policies that respond to the channel's unknown behavior. So the outline of this talk will be the following. I'll first motivate it with a learning problem where we'll be trying to schedule optimal matchings in the network in a distributed method. So we'll turn to greedy algorithms for that. I'll give you a distributed learning algorithm that's able to accomplish this, and then derive novel bounds on the performance of these algorithms. I'll then show how these algorithms can be put into applications where networks get stochastic arrivals, where we're trying to now stabilize the network's queues in order to service traffic demand, before giving simulation results and concluding with some final remarks. All right, so the problem setup. Our objective is the following. We're given a graph G, which consists of a node set N and an edge set E. Time is slotted and proceeds in discrete increments, and we'll index time using 1, 2, 3 to infinity. In this work, we're going to focus on the primary interference model. Under primary interference, edges that share a node cannot be simultaneously activated and cannot simultaneously transmit at the same time. As a result, activation sets have to correspond to graph matchings in the network. This is a model that's been well considered in the literature. I don't provide a list here of all citations in the paper I do, but it well models spread spectrum communications, directional antenna systems where the primary constraint is that you cannot simultaneously transmit or receive from more than one other node at a given time. We begin by devising algorithms for finding best matching when the edges have stochastic weights. Later, we're going to move into showing how we can then use this as a black box to stabilize networks. For each edge E, we'll consider a reward WTE that is IAD over time with some mean, which we'll denote W bar E. Now, at each time T, we'll basically go through 3 steps. First, we'll choose an activation set, a matching in the graph. We will then observe the weight at that time T for each of the edges that are in our chosen matching. And finally, we'll obtain a reward, which is the accumulation of all weights that find themselves in this matching. Now, if we let M script be the set of all graph matchings, we know that the optimum matching, the maximum weighted matching, M star, will be the matching that basically has the greatest summation of average weights in the graph. However, in general, finding M star requires centralized control. And it's quite complex. So in this work, we're going to focus on finding greedy maximal matchings. It's a well-known result that greedy maximal matchings provide a 1/2 approximation of the maximum weighted matching, and in general actually perform much better than that. Additionally, there exists very simple distributed algorithms for finding greedy maximal matchings, and we'll use this to our advantage to kind of create nice distributed algorithms for stabilizing our networks. Learning greedy activations. We consider activation sets that are constructed greedily, and this algorithm is due to Price in 1999. It begins as follows. We start with kind of the set of all edges in the graph, and this matching set which begins as a null set. We then iteratively, until we have no more edges that can be added to the matching, we choose an edge that is locally heaviest in E. By locally heaviest, I mean that A, it does not conflict with a edge that's already been added to the matching, and it's better than all other edges that could still be added to the matching that it conflicts with. So any other edge that shares a node with this edge, if this edge is better than all of them, it gets to be added to the matching. We'll then add it to the matching. We'll remove all adjacent edges that share a node with that edge from consideration, and we'll keep doing this until we can't consider anyone to be added to the matching anymore. Now, if we knew the actual mean capacities W bar E, we could plug it into this algorithm, and we could obtain a 1/2 approximation of our maximum weighted matching M star. And indeed, we'll define the offline greedy solution to be M naught, which is the matching that's constructed through this method. Note that this method can easily be made distributed with very low message passing complexity. This is due to Hopman in 2004, and basically what is shown is that if you communicate kind of over a side channel, you can tell your neighbors that they're the best neighbor that you want to match with, and if that neighbor wants to match with you, you form a matching and tell all your neighbors to drop you from consideration. And if you iteratively do this, you'll be able to basically construct the greedy maximal matching in a very distributed, easy method. However, in this work, we do not know the sample means W bar E, and we'll need to learn them through observation. This introduces an exploration-exploitation trade-off. We want to schedule the best activations that we have found so far, but also want to try other activations to possibly find a better one. Now, our problem is related to the stochastic multi-arm bandit problem. In the stochastic multi-arm bandit, basically there consists a set of actions that you can take. Each one provides an IID reward, and your objective is basically to learn which action maximizes your reward over time. Except in this work, we're actually considering combinatorial constraints. We can now pull multiple edges subject to a combinatorial constraint, namely the matching constraint. Now, combinatorial multi-arm bandits have been well considered in the literature all the way back to 2012. And recent work all the way to the present has kind of improved upon the bounds that they give. And the best known result that exists right now is that, in general, the performance of these algorithms with respect to regret, which I'll show you in a second, is 1 over delta KL log n, where K is the number of objects that can be added to any combinatorial constraint, L is the number of objects period, and delta is the difference between the best and second best combination. As in previous work, we're going to use upper confidence bound weights to basically trade off our exploration-exploitation trade-off. UCB weights consist of basically 2 components. The first component will be a sample mean based off of which we denote W hat T, which is basically a sample mean of all observations we've made of that edge so far, plus an additional term, which is an exploration term, which consists of the square root 2 log T over T, where TE is the number of times we've observed that edge so far. Note that in general, if we don't sample some edge at least logarithmically in time, this exploration term blows up and we start to sample that edge. This captures the principle of optimism in the face of uncertainty and has been pioneered all the way back to 1985 and is well considered in the bandit literature with improved methods being discovered even to today. All right, so to embed this in our greedy activation sets, we'll consider the following algorithm. We'll have a sample mean for every edge, along with the number of times that we've sampled that edge so far. At each time t, we'll basically construct our UCB weights and then feed those UCB weights to our greedy maximal matching algorithm. We'll then observe the reward of all the edges that are in the returned matching. We'll update our sample mean, along with updating the number of times that we've seen those edges, since we've seen them once more, and basically then iterate over that process throughout time. All right, so to analyze the performance of this method, we introduce regret. And specifically, we'll look at the regret with respect to the offline solution. So regret is defined, in this case, as the expected difference between the offline solution that always chooses the maximum weighted matching versus our learning algorithm that's going to, over time, choose different matchings as it learns the best set of activation sets. we use a new bound, a novel bound for this. In general, the upper part is probably not super informative. What's more interesting is actually the limiting behavior, where we see that the regret divided by log n over time scales linearly with the cardinality of the edge set, and inversely with delta squared min, where delta squared min is the difference in expectation of two adjacent edges, the minimum difference between them. All right, to give some intuition as to where this bound comes from, note that an edge can be added to our matching that isn't in the offline solution because of two general reasons. First, there's an estimation error between it and a neighbor. Basically, that edge thinks it's better than its neighbor when it really isn't. The second case is that it's actually promoted into the matching. For instance, another neighbor of that edge could think that it's better than that edge, remove that edge from consideration, and our edge gets promoted into the matching. Now, in general, in most greedy combinatorial algorithms, this could be a very costly mistake. It could send us down basically a cascade of decisions that would accrue kind of regret at each decision point. What's interesting about the maximum weighted matching, or the greedy maximum matching problem, is that we're not going to face that problem. And the reason why is because each edge in MT can be adjacent to at most two edges in the offline solution. So as a result, if you are promoted over one of your neighbors, there is a cost that you may incur from taking out another neighbor, your other neighboring edge, but your other neighboring edge could only be taken out if you thought you were better than it, which is a rare event, or because you're better than it, in which case there is no cost to be incurred. So the second question we can ask is, well, we have this delta squared min term in our regret bound. And we know from the stochastic multi-arm bandit problem that there's a delta min term, so there's no squared in it. So one question we could ask is, could we improve upon our bound? Is this just lazy analysis? And the answer is no. In fact, there exists a graph G and a specified set of edge weights such that we can show that the online algorithm is up to a constant tight with our upper bound. And the graph that achieves this basically consists of a bunch of disconnected components consisting of three edges in each connected component, where the two external edges have a mean weight of 0.5, and the internal edge has a mean weight of 0.5 minus delta. Now, one of the problems with the greedy maximal matching algorithm is that it doesn't really see the big picture. So it kind of just greedily adds edges to the matching without stepping back and asking if this is really the right thing to do. As a result of this, it has a hard time deciding whether or not it wants the internal edges or the external edges. If we step back, we'd see that there was no problem. We obviously want the external edges because there's two of them. But the greedy maximal matching algorithm can't see that, and as a result, it incurs extra cost from that decision process, which gives us our delta squared in turn. All right. So we next turn to embedding our learning problem in scheduling problems. So we'll now slightly change our problem and look at a graph again that consists of a node set and an edge set. But now each edge has an arrival rate of packets to it, which will denote lambda e. That's IID over time. Additionally, each edge has a capacity, which will denote CTE at time t, which is IID with some mean C bar e. And we'll see our weights emerge out of this in a second. Now, we define the stability region of our graph that we're given to be the set of all arrival rates that may be stabilized. And it's well known from Tessalus and Epimenides, 1992, that the optimal policy is to schedule at time t the maximum weighted matching, where each edge is weighted by the product of its Q backlog multiplied by the mean capacity of that edge. But again, we don't know the mean capacity of the edges. Additionally, it's well known that if we schedule greedy maximal matchings, we'll achieve a 1/2 approximation of the maximum weighted matching, which means that we'll be able to stabilize half of the stability region. So any arrival rate such that 2 times that arrival rate is in the stability region can be stabilized through the use of greedy maximal matchings. So to embed our learning algorithm, we consider a frame-based max weight policy. And the way that this policy works is that we chunk up time into frames of length k time slots. At the kth boundary, we take a snapshot of the Q backlog and basically freeze it in time. Then we say that the edge weights are WTE, which we looked at from our previous learning algorithm, is equal to the product of the queue backlog times the observations that we observe of that edge divided by the maximum backlog that we took a snapshot of. Now, for stability, we will need negative Lyapunov drift between the frame boundaries. And if we knew the mean edge weights, we could solve for the activation set, either optimally or approximately, and apply it at each time slot throughout the frame to achieve this. Since we need to learn the activation set, however, we're going to lose some service over the frame. So we have to show that this loss is not too great and decays rapidly enough for us to have negative drift. And indeed, if this loss is sublinear over time, then a large enough frame size, this loss will be negligible and we'll have negative drift. Okay, so the main theorem then is that for any arrival rate vector within the half stability region, there exists a sufficiently large frame size such that the frame-based max weight algorithm can stabilize the network. To prove the negative drift over the frame boundaries, we define the regret with respect to the approximation ratio. Now note that instead of looking at the expected difference between the offline algorithm and our learning algorithm, we're going to compare it with respect to 1/2 of the maximum weighted matching and our learning algorithm. Now for the distributed greedy algorithm that we previously gave, we can show the following bound on regret, which is novel. And the important thing really here is that we see that the regret scales sublinearly over time. And as a result, if we take a frame length that's sufficiently large, the surface rate of the frame will approach the 1/2 approximation of M star, and will induce negative drift, and we'll be able to stabilize our network. So we give simulation results of this. In the first case, we consider a 4x4 grid graph G with Bernoulli, this should, sorry, say CTE, not WTE, but with capacity CTE that are IAD over time. We'll consider a uniform arrival rate to each edge, and we'll assume that in this problem, the mean capacities of the edges were chosen randomly. And I don't show them up there. However, what we can see is that the offline greedy maximum matching performs very well. In fact, we can devise an upper bound for this, which is not shown here. We can show that the greedy maximum matching that knows the edge capacities is able to achieve almost the complete stability region. And we see that our learning algorithm with increasing frame sizes is able to approach the solution of the offline greedy maximum matching. This kind of gives us a nice warm and fuzzy feeling, but there is one kind of problem with this approach, namely we're relearning the edge capacities over time at each frame, where in this problem they're not really changing. So in our next simulation result, we showed that we're actually able to use this method to track changing mean edge capacities over time. Again, we consider our 4x4 grid graph, but now we're going to assume that the means change according to a Markov chain with some very small delta. And namely, when it's in the low capacity state, it'll be a Bernoulli process with probability of success 0.25, and in the high capacity regime, we'll have probability of success 0.75. We have an arrival rate then to every edge equal to 0.07, and we plot basically how well the offline greedy maximum matching algorithm does relative to our learning algorithm. Now we can construct a lower bound on the capacity, and what's interesting is we see that as the capacity of the network drops periodically below our 0.07 arrival rate, our queue backlogs blow up, but we're able to stabilize the network then once we get back into a high capacity regime, and the learning algorithm tracks the offline solution pretty well with a slightly higher queue backlog. So in conclusion, in order to service stochastic traffic demand, wireless networks must take into account their channel capacities. In this work, we devised distributed learning algorithms for adapting to unknown channel capacities and derived novel bounds on the performance of our learning algorithms. We showed how they can be embedded in frame-based control algorithms to stabilize the network where they're used as a black box. And we provide simulation results to show how our method can track changing channel statistics over time. As a final note, in subsequent work, which appears in my thesis, we've extended our results to networks with general conflict graphs as well. For instance, like two-hop networks. So anyways, that's all. So now we'll open the floor to questions.
Any questions?